Hi everyone. In the last session we made the geometry in SpaceClaim, and in this session we will be making the same geometry using AutoCAD software, and then from the AutoCAD software we will export it to the workbench environment. So beginning in AutoCAD, as you can see, the first thing that because this will be a 3D model, so we should move to 3D modeling. Initially when we start the software, it is in drafting and annotations. We will move to 3D modeling, and now before beginning we should save our work. So we can save as, and in our working directory, so we'll name this model as model 2. So since this is our model, we will be making the full cell model, and like previously we did, the fuel will be flowing in the positive x direction and the oxygen will be flowing in the y direction. So this xy plane, sorry, the oxygen will be flowing in the z direction, and the xy plane, sorry, the xz plane is the electrolyte surface. So to begin, we should change the units. So we can change the units by directly typing in the command units, and it will take us to the drawing units section, where we can change it to millimeters. There's also an option of micrometers, nanometers, microns. Nanometers, microns. We can go to microns, but we don't need to go to microns. We can still draw a good geometry using millimeters. So we'll keep in millimeters. Okay. The other way we can go into the unit section is by going to the options. Sorry, not this. From here we can select drawing utilities and units, and if you go to the units you get the same dialog box, and the precision, make sure that we have good enough precision to go to the microns. Now we will, as we stated earlier, y is on the top side, in the positive y direction will be the cathode side, and the negative y direction will be the anode side. So once we draw the electrolyte, we will start by going towards the positive y direction, and in the positive y direction we have the cathode side. So the first cathode layer is 10 microns thick, and that is actually, I'll show you again. So this is the distribution of the layers that we have, and we will not be modeling the electrolyte and the interlayer. So we will be modeling directly the CFL and the CCL, cathode functional layer and the cathode current collecting layer. From here we should start the modeling, and for modeling we can directly start from draw section. Notice that this is different compared to the drafting. In the drafting we have these options over here, but since this is 3D modeling, so we have got other useful tools also, that is for coordinates and views, but the drawing section is limited. You can have a rectangle and we can give the command 0, 0. It is better to draw the, like we did previously in the SpaceClaim, we can draw in the XY plane, draw all the cross sections, and then since this is XZ plane, see, and we want to extrude those in the positive y direction, so we will draw the sorry, we will extrude them in the positive x direction. So we will draw all the layers in the YZ plane, and drawing in the YZ plane, we will extrude them in the positive x direction. To begin with, we can actually draw our model in the xy plane in the initial front. Oh, sorry. And then extrude it in the positive z direction. So if you look at like this, so this is the initial orientation when we started, and we can draw all the layers as rectangles over here. So we've given the command rectangle and specify 0, 0, and it is important to note that we can actually give the other dimension. It is not a parametric, so whatever dimension we give, we cannot modify it later. So the x-axis is 9, it is in mm, so it is directly 19, and comma, and the next coordinate, since this is 10 microns, so this is equal to 0.01. So the next will be 0.01 mm, and we got a very slim or thin layer. Now we need to draw another rectangle, and again the coordinate will be 19 cross, and we can give at the rate of 0.01, or sorry, at the rate of 19 comma 0.01. So yeah, at the rate of gives like from that relative coordinate system. So now we have modeled the CFL, CCL, and then we have got the meshes. So the mesh, the we have got the mesh of 0.3 mm on the cathode side, again at the rate of 19 0.3 mm, and on towards the anode side we have first the anode functional layer, the AFL, that is the anode functional layer. So we'll draw another rectangle that is 0.0, 0, and now we will give at the rate of 19 comma in the negative direction 0.007, that's only 7 micron. Yeah. Now the rectangle, that is the, this is actually the anode support layer, and the anode support layer is 1 mm, so we will give at the rate of 19 comma -1, and we have a mesh again, so we'll go to a rectangle, and this side again at the rate of 19 comma in the negative direction 0.5 mm. So now these are all the layers of the fuel cell that we will that are needed for with plane extrusion, and we will extrude them in positive z direction for 19 mm. So you can given the command ext and 19, again ext 19. Keep in mind that using the spacebar, it's there, keep reading the commands, and spacebar is considered as an enter in the AutoCAD environment. Now we can have different layers. This is very helpful. This is very helpful to get, we can add different layers so that once we are working in one layer we can hide the others. We can directly go to the layer properties and add names for all these layers. So we can add new layer. Do not rename the zero because we need some construction that we can always do in the zero layer, and we will add this as CFL, cathode functional layer, and another new layer for CCCL. It's not necessary that we create all layers. It's just helping in modeling. When we need to create the layers properly, that will be during the meshing. We can just have one layer for the meshes and just one layer for the manifold or gas channels, and the interconnects. Okay, with this being done, we can give different colors to the layers. Also CFL we can have in the red, cathode functional layer we can have it brown, the current collecting layer we can have blue, anode functional layer we can have some green, support layer we can have some yellow shade, the meshes we can have some gray, and the gas channels again. So this is to make the clarity in where we are modeling. And the interconnects we can again have gray. Okay. So with these we can continue with the modeling. And now we will select each component and shift it to its correct layer. So at the top is the mesh, so we will move it to meshes, and at the bottom also this is a mesh. Now this is the anode support layer. Above the anode support layer is the anode functional layer. There is a cathode functional layer, and this is better understand visually. It is better if you go to conceptual shading. Now we can see it in a better format. Oh, it converted all to ASL. No, this is a part of mesh. This is also mesh. This is a node support layer. I think we should change the color for the meshes. It's in transparency, I think. So now we have a full model for the layers, and we need to make the gas channels and the interconnect. For making the gas channel, we'll first go towards the cathode side, and we need to make the gas channels towards the positive Z direction. And we should keep in mind that the gas channels, actually if we array them, we cannot make them into a single component. or a single part. These are all different parts. Turn off the grid, and now we can. Now the best part for moving on to AutoCAD is the ability to use UCS, and it helps in modeling a lot. So we can move our UCS or the coordinate system to any point where we like, and change the orientation of the XY plane also. So we'll rotate about X, and settings. So this is 0.5 mm, so we'll take it 0.05 mm snap. Oh. So now we have the XY coordinate system. Sorry, we should go back to the global. So we need to draw the rectangles in the positive Z direction, so it is already in XY plane, so we just need to shift it. We'll just shift it into this direction. Whichever surface it is highlighting, it puts the XY plane in with aligned to that surface. And when we give the command rectangle, make sure you're not highlighting any surface. So give a command 0,0, and now at the rate, or we can give in, it will be -1 and y is 1, and we can extrude it. We want to extrude it in 19 mm, but in negative direction. Make it ortho and give 2, 4, 6, 8, 10, 12. So we have manually copied all of them because we need to union them afterwards, and if we array them we cannot union them. So it is important that we keep in mind that we will copy each gas channel individually. And right now we just need to modify. If we go back in the, now we need to add the inlet and the outlet for the gas channels, which we will do right now. And but before that we should change the orientation. So we'll, yes, so we get the orientation, and we give the command L from 0,0, and we can turn off ortho. But even if we want ortho, just press the shift key and we get ortho. Give 1, oh sorry, 1, and now we want to draw a arc, so we can have start, end, and angle. It follows the from x to y. We should check which. So from the start point will be the, because if you take the right hand, according to the right hand, adjust your thumb to the z axis from x to y, so the arc will go in the clockwise direction. So it's always being modeled in the xy direction, so we should, the start is 0, 0, this will be the end, and I think we give the angle start and radius, so you give 0, 0, this is the end, and now again arc, delete the lines. You can add a line, so you can shift this origin and minus, in the x direction we want to move minus 9.5 because this is half of 19 mm, sorry, 9.5, and we will add a line over here, that this should be a construction line. We want a vertical, and now mirror. Erase source objects, no, and now add a line to join them. Now the easy part is that we can hide all others except for our current 0, and as you can see all the other geometry items are hidden. Now you can add a line again, this point to this point, and in order to extrude it we first need to make a region. You can make a region, this is the command for region, and select all the lines. So now the region is created, so we can extrude it now in 1 mm. The 1 mm is in opposite direction, so Control Z, extrude it -1. Okay, now we can mirror it again in likewise like we mirrored 1, so we can mirror the whole 3D object also. So we'll use the mirror command and move our coordinate system, and So we're at the center, and now again a horizontal vertical construction line. So we'll make a construction line, but this time horizontal, and it passes through the origin 0, 0. You got a construction line. So now we can mirror it. Now we can union all these parts, select them manually. If we miss a part, we can always union them again, and enter. Now this is one part, and since this is a gas channel, so we can move it to the gas channel. The last part is the interconnect on the cathode side. So let's go back to the global coordinate system, and now we will move on to the top of this point. So we will just move along until this point, and xy coordinate we should rotate about x. Yes. Again rectangle 0, and the height of the interconnect is 0.5 mm, so giving 19 comma 0.5. We should add other rectangles also right now. This will be the top layer, and we can add a rectangle here also. Make sure while making the rectangle that this surface should be highlighted, otherwise it will select some other orientation for making it, and we can extrude it till this point and now copy it again. And now extrude the, we will extrude it by 19 mm. Like previously, we will keep in 0 and hide all other layers, and now union all these geometries. Now you see the lines between these geometries, they have finished, making it a single geometric entity. We can move this to the interconnects. We should enter the gas channels. With this we have, and we are seeing the construction lines. It's not moved properly, so we should move it to the interconnect, and now we can turn off. So you see that we have got made the cathode side completed, and now we want to mirror it towards the anode side also. And to mirror it, we can do a it's easy to mirror it to any, to just the offside, rotate it to the proper orientation and then move it to couple with this surface. So we will first make our coordinate selection the global. Now we will mirror the geometric entities for interconnect and the gas channel. So give the command mirror, select both of these entities and space. So the first point of the mirror line, we can give it directly 0, 0, and it's too shallow. Okay, we should move the coordinate system below. So we can move the coordinate system to this point, and now mirror again. And the first line is 0, 0, and if we go to the second point, this is ortho selected, so it will definitely have a 0 degree, and you can give any point. The next step is to give a proper orientation, because they are not in the same direction. We want that the anode side, the hydrogen fuel flow direction is the positive x direction, so we need to rotate it by 90 degrees, and but the rotation axis is also at the center, so we should first take the orientation have the snap. Okay, now we'll move 9.5 and 9.5 mm to get into the center, so we'll move again 9.5 comma 9.5 comma 0. So now we are at the center, and to rotate it we can just need to give the command rotate. Base point is 0, 0, 0, and you see that -90 degree rotation. That's okay. Finally we will move our these two geometries, move it to match the surface, so we can either measure it and then move it, or we can just directly move it. So you can move these geometries, give the command move, and we want to this endpoint should be matching with Yes, make sure to be careful that we don't select some other point. And now we have got a beautiful geometry already, and we can now is a good time to save it. So save the project. So there are two ways of exporting it to Ansys environment. The first is directly by the drawing file, and the other way is to export it to the IGES format. So we'll export it to other formats also, and IGES is already selected in the AutoCAD domain in the AutoCAD folder. So I made it full cell model2.iges. Save. And now it's asking for all the, make sure that we have selected all the layers, and now it has exported to IGES format. Now we can go and take a look at the space claim. In space claim, now to import it, we again have to import it starting from the same mesh. So bring one mesh in, double click the mesh to get a different row, and then you can have another column here. So in the first, we will be importing directly using the AutoCAD geometry. So we'll have AutoCAD model, and the other we can have the AutoCAD model by IGS. IG from IGS, and here we'll go to space claim geometry. Now we can go to file and directly import it. So we can, to import it, we can directly go open, and to open the file we just need to select for all supported files we'll direct full cell model 2. And now you see we have all the solids aligned, and we've got all the model geometries as solid. So whatever there was in the all the more geometries that were separate to each other, now they are separate solid over here. So we can have solid 1, solid 2, keep and check that all the geometries are consistent. Now the last part is again to prepare it for going to the meshing. We need to share the topology, and for sharing the topology, make sure that the coincidence tolerance is way less than the minimum thickness of the layers. So by default it is 0.0095 mm. That makes about 0.01 micron, 0.01 mm. This is almost 0.01 mm. This is still because the minimum layer thickness, we have the AFL, and the AFL is actually 7 microns thick, right? So it will not be able to do it to share the topology, or it has made it a single geometry. It's definitely not a single geometry. We should check all the layers. You can see the shared topology over here. So there will be 1, 2, 3 boundaries, means there will be 5. Okay, I think we should decrease it. Point that this will be equal to 5 micron. Yes, now we have got more number of layers, because if this is less than the coincidence geometry, if this tolerance is less, then we will be missing one object, or it will cause more problems afterwards. So now everything checks out, so you can click the correct yes button, and now it's ready to go for the meshing. So this is the first way that we can directly import, but um, let me discuss one more thing, that we should always first check the dimensions. So we should go to the measure and measure any length, any representative length, to make sure that we got the correct import dimensions. This is 19 mm, this is 19 mm, 0.5, so this all checks out correctly. So all these things are correct, so we can move on and move towards the meshing. And the next part is going to, for the IGS, again we will open the geometry by space claim. Okay, it opens in discovery. We can right click and open in space claim. So now again we can open it and also put it files for IGS. Now since our the final coordinate axis, when we were in this coordinate system when we imported it, so we should make we should be cautious about the coordinate system also, but that's not that important. Now we have different components for each layer when we import through IGES format, and we should measure it. So this is 19 mm, this is also 19 mm, so the dimensions are okay, and as a final step we should share it. Again we get 0.0095. 134 faces, and if we give it now it's 135 faces. So that means we're gonna miss one face if we give an improper tolerance. Better to go even less to 1 micron, but there will be no difference now, and we can give it okay. So this is the full methodology for importing the geometry from AutoCAD module to Ansys Workbench, and we can close it. So now we imported the geometry from the AutoCAD model directly also, and by converting through IGES also.